So this session is about non-terrestrial connectivity solutions, and particularly the TIP working group. And we have three panelists here to speak with us today. We have Erik Kline of Aalyria Technologies, Frank Patry of Omnispace, and Luca Lodigiani of Inmarsat. And I'm Dan Dumitriu. I actually work for Sony Semiconductors, so I'm very much the oddball out here, but I'm learning a lot, and perhaps you will too. I mean, I'm sure you will. Okay. Oh, yeah. So, first, a quick intro to the non-terrestrial connectivity group, and I'll let Frank take this one, since he knows more about it than I do.
Yes. How do you turn this on? Hi. The NTCS is one of the subgroups that participates with Infra project, and really our focus is extending, the ecosystem from the terrestrial world to the non-terrestrial, whether that be HAPS, UAV, satellite systems. So the goal is to reap a lot of the benefits that we're seeing the terrestrial community accrue from the open RAN disaggregation and how that accelerates innovation in business, and try to get that to work effectively in the domain that we're working in. Next.
Oh, sorry.
And really, our near-term mission and deliverables is to really establish, solutions, some use cases around the O-RAN and how it would support us so that we can start to prove in a lab environment with the vendor community that they have the ability to take their terrestrial type solutions, extend it to the non-terrestrial, and then actually work with the TIP folks to get badged, showing that they're compliant and capable. And this is kind of the big picture showing that, our reach is very broad, from the large geostationary assets to the LEO layer and all of the different user equipment and applications that at one time when we get the 5G and full 6G should be completely integrated from an end user experience. Whether you're terrestrial, low or high Earth, you should be able to get the same, experience, the same services, and we're hoping with the O-RAN and the integration and disaggregation that the satellite and the HAPS world will experience the same amount of cost reduction, operational efficiencies, and quicker to market with new innovative products and services. I'm not going to really deep dive into this, but this kind of shows you the framework for how the O-RAN overlays into the non-terrestrial world and the interfaces that we're focusing on, and how we're looking at both the management and orchestration layer and the real-time type interface to the eNode Bs and the RAN equipment providing the actual transport of the bits to and from.
Okay, so now we'll have a brief presentation from each of the panelists, and first up is Erik.
Thank you. Thank you very much. Hello, my name is Erik Kline. I am with Aalyria. We are a new Silicon Valley-backed startup, and let's see here. Does this work? There we go. Yes. And our mission is connectivity everywhere. So we presently comprise two technologies with a heritage of development and deployment at Alphabet. One is an atmospheric laser communications technology, and another is a software platform for orchestrating networks across all domains, land, sea, air, and space. It had its origins, the orchestration platform had its origins in some Google internal efforts, but it was fully operational for running Loon's high altitude platform network, or HAPS network, or Stratolites as we called them sometimes. The atmospheric laser communications platform we call Tightbeam. I am not a laser physicist, but this stuff is very cool. If anybody has questions, I can try to get you connected answers afterwards. What I'm here to talk about really is our network orchestration platform that we call Spacetime. It is a service management and orchestration platform, an SMO. Traditional SMO functionality is focused, I think, largely on operating terrestrial networks of essentially fixed assets Only the UEs and mobile devices are the ones that are really moving. Towers and G-Node Bs don't often move. And existing solutions may typically not be well suited for deployments where the network infrastructure itself is in motion, continuously dynamic orbital LEO constellations, for example. But for Loon, the floating stratospheric cell towers were definitely moving, which meant their backhaul connectivity to each other was also definitely moving. And we needed to take into account for many changing physical world constraints. So we built something to orchestrate our own non-terrestrial network. And so Aalyria's space-time network orchestration platform models the physical world. It understands the physics of moving bodies, antenna patterns pointing, channel use, and power levels. And it orchestrates network topologies that meet the requested connectivity service requirements. It keeps evaluating predicted motion, obstruction masks, signal propagation like weather, and so on and so forth into the future. And it programs these new topologies well in advance of their predicted need. We currently have support for an RAPS-style integration. Our APIs are not yet ORAN compliant, they're gRPC-based. But you have considerable access through the northbound interface to most of the internal state, including we have some apps that monitor modeled versus measured capability for links, so you can do machine learning on link formation, what's working, what's not working. We actually discovered that somebody had built a billboard at one of our ground stations on Loon that was obstructing, that was not represented on the obstruction mask by observing the system, telling us that this link was always failing in this direction. But the other thing that we have that you can use, that uses our NBI, is we've built this UI that makes all of this information intuitively visible for the network operators. You can see the physical topology, you can see the relationship to the logical network topology, you can overlay weather and drag time forward and backward, and you can inspect obstruction masks, so you can answer questions like, why is the topology the way it is? Maybe there was routing around some weather event, or maybe, what looks like a topology that you thought you could build, you couldn't build because that would have required putting a beam directly through a building, which is generally considered bad. And so you can generally drill down on any of the elements in the node there. So that's just a brief overview of Aalyria. And so I think that's me. Thank you.
Okay, so thank you very much. My name is Luca Lodigiani. I'm a principal systems architect in Inmarsat's network architecture team in the technology office. So Inmarsat, you may or may not have heard of us. We are a long-standing satellite operator. We've been operating since 1979, so we're pretty long-standing service. And today we have an active constellation of 15 geostationary satellites, with more geostationary and non-geostationary satellites coming into service. And we provide essentially global scale services. So if you have ever flown on an aircraft with in-flight Wi-Fi, there is a good chance that it was backed by our network. The cockpit connectivity is definitely, most cases, backed by our network. We provide safety at sea communication, so for ships that are in distress, they can send signals through our satellite network. And we have staff basically across the world, so we're pretty large operator, and we are starting to foray into adopting the implementation of non-terrestrial network that has been enabled by 3GPP release 17 to provide in the future services direct to handset and our 5G enabled services via satellite, both direct and indirect through backhaul. So our current constellation is basically, as I said, of 15 geostationary satellites. We have HEO, high elliptical orbit, Arctic satellites that are coming into service in the next couple of years that will serve the polar regions. We have air to ground. We have if you're flying over Europe, the in-flight Wi-Fi is probably supplied by our air-to-ground network in partnership with Deutsche Telekom. which is the European Aviation Network, and we have plans for future LEO constellation to integrate with our existing satellites. We are split between a global L-band, which is now band 255 in 3GPP, regional S-band, primarily over Europe, and 255, and Ka-band, which is actually undergoing works in 3GPP for standardization. So you will see also this band available for NTN access in the future. And that's basically it. Thank you very much.
All right, Frank? The clicker.
Sorry.
Hi, I'm Frank Patry. I'm the CIO at Omnispace. Omnispace, like Inmarsat, we're a satellite operator. The difference is we're a new entrant, a startup, really focusing on building the 5G NTN LEO constellation. And our goal is to really build the first standards-based, out-of-the-box solution that kind of does hybrid between mobile network operators and the satellite operator, where we're basically a roaming partner in the sky using all the standard interfaces today that terrestrial roaming uses, and operating the 5G NTN NR over the satellite. This is kind of our positioning from the perspective of how we complement the mobile network operators inside of the cities. They're using terrestrial, their own spectrum, their own bands, and as soon as they exit out of the coverage area of the existing terrestrial footprint, they seamlessly roam, like you do today when you travel around the world, using the standard interfaces, standard handsets, and everything should work correctly all the way through the billing and invoicing. We're looking at the standard services and customers, either voice data IoT, and then in the customer base, it's government, enterprise, consumer. But our focus is to provide those touch points through the home network. Our goal is not to be a direct to any of those consumers, any of those customers, but to allow them to just add the satellite functionality to their existing handset through their home network and allow them to seamlessly access non-terrestrial services. This then allows all of the different opportunities you see in the market that the current mobile network operators are providing at a terrestrial level, the agriculture and all that. But once you get out of reach, you really want your tractors to be able to send telemetry over the satellite so that your monitoring of your farm operations is seamless. Same thing with connected car for software updates, et cetera. It is 3GPP standards. We have spectrum that's globally, allocated to us, and we should be able to seamlessly integrate as a roaming partner the same way terrestrial partners do. Easy onboarding. That's really my overview, and the reason that I am participating with this group is we would like to leverage the O-RAN initiatives that our M&O partners are embracing to reduce their complexity, to provide services quicker, so that we can then extend that to our network so those services and products can quickly show up in the NTN space for their customers.
Thank you. All right. So I'm Dan Dumitriu, and I'm the odd man out here because I'm not working for a satellite company or a telco. I work for Sony Semiconductor Solutions, and we actually are building an IoT platform mainly for vision-based sensors, because you may or may not know Sony is actually a market leader in CMOS sensors for cameras. So there's this new business unit we're building out now to create essentially ubiquitous sensors for various types of verticals, like many of those things that Frank just mentioned. Vision can be an asset as well. And so what we're doing for this was we're building these devices that essentially have a CMOS sensor, and then they're programmable over the air and connected to the cloud, essentially feeding telemetry, typically derived data that's computed directly on the device. We are generally agnostic to the connectivity. Some use cases don't move around and they have fixed power, so it doesn't matter, it could be Ethernet connected or Wi-Fi in a lot of cases. But also we are going to add cellular, probably NB-IoT. We have another sister company within Sony Group makes cellular IoT modems, basically, so we can put that onto our platform. So essentially, we do this, optimization of software for a variety of devices because they may be built using different microcontrollers, and we do the lifecycle management of the applications which are running on these sensing devices, so that only the very specific data that we want coming out of them comes out. So this is pretty much like our, I just put this on here. Just in case you're interested, you can probably find the slides later, but essentially this is like, we've developed this entire device stack for an IoT, programmable IoT device, which in some ways it looks a little bit like what Android looks like, I mean, maybe they all look the same, but essentially the idea is to make it very programmable by a third party because we're not targeting any specific vertical. It's really like meant to be a generalized solution. Okay. So, the ecosystem for us, includes a lot of different things, including connectivity. Also, we're working with some telcos, working with Docomo in Japan on POC to basically dynamically control network QoS when in certain applications. And I don't know if you heard of this project called Camara, which is an API that's supposed to be like a telco agnostic API for doing this sort of resource management. And also a lot of these Linux Foundation projects that are relevant for us. And that's all. So let's move on to the panel discussion now. I've learned a lot just talking to these guys over lunch, and I guess you will too. So here we go. Okay, I'm gonna get my question list out. Since, okay. All right. So first question: what are the main factors that are driving Open RAN for NTN? Like, why does NTN need Open RAN? So, who wants to take that first?
Yeah, I'll give it a shot. I think that you saw some of the complexities that NTN, adds to the equation from what Erik showed, the platform they had to build to track things moving and the issues that you have with things that move while the satellites move, like airplanes. So we would like to use the O-RAN functionality that's being developed for the terrestrial set of operators to manage our G-Node B in space. But then in addition, have the additional orchestration and management functions and RIC functions to handle the complexity of moving base stations, changing spectrum allocations country by country, and the ability to do cross-satellite or inter-satellite links for dynamic routing. So it's a next level routing problem that you would see from a terrestrial operator that is common among the LEO and the MEO and GEO NTN players. So we believe that if a set of common applications and platforms for managing the complexity of that, including collision avoidance, could be defined and implemented, it could be used by any of the satellite operators as a common platform, much like some of the common OSS platforms that exist today in the MNO world. So we think it's a big win to get a consistent management and operations implementation that is shareable and extensible by the operators around the world.
Yeah, I can perhaps add a bit more color as well from our perspective. So to me, there are multiple dimensions in which the ORAN and Open RAN mindset and ecosystem and the architecture and interfaces can benefit us also to a fairly low level. So historically, some of the air interfaces that we use in our current systems, some of them we even designed ourselves, and that has served us well until now, but now we're seeing the benefit of aligning with what's coming on with NTN, both in the 5G NTN space, but also narrowband IoT. And we have seen that this can deliver value already today to direct to device. However, one of the bigger benefits is also when you start operating, and you may have seen it from the slide that I presented. So today we have primarily GEO systems. They are primarily transparent band pipe systems. But in the future, we're going to have non-geostationary LEO, perhaps even regenerative systems. basically being able to build a common RAN both on the ground with components in space. So basically using the ORAN, both a mix of the 3GPP, ORAN, or even SCF, like the FAPI and FAPI interfaces, to disaggregate the RAN and basically choose which components to place where. Perhaps having a common CU-DU function for a GEO and LEO system, and then have different RUs that operate different spectrum bands in the feeder links, or even have parts of the RU and the DU on the satellite itself. Or even within the payload itself, using some of these disaggregation interfaces to plug in components from different vendors, to plug in multi-access functions for user link, multi-beam, feeder link, or even interplane links. These are things that we think the Open RAN and the ORAN ecosystem can enable. And going back also on the orchestration, spectrum management, I mean, down to the implementation of the RAN, the reality is that operating space-based communication systems is very different from operating terrestrial systems from a spectrum management, radio resource management, interference management, routing and mobility perspective. Mm-hmm. So being able to, say, have a RIC that allows you to plug in a NTN beam mobility API, XApp, that, for example, manages UE mobility across beams, or even in a LEO system, you will have this problem that with the moving G node Bs, moving E node Bs, you have UEs that may be stationary on the ground, but you have the satellites orbiting over, so you have constant handovers, or you maybe have beam forming that allows you to track the users. But at the same time, all of that complexity needs to be managed. In a monolithic system, it's very difficult to do. We have extensive experience and IPR built up from the years that we've been operating our existing systems. So what we want to be able to do is essentially take the 5G, 3GPP architecture, the ORAN architecture, and plug all of these control algorithms and primitives into the system.
Yeah, just to emphasize the importance of that, if we don't have a common framework that's shareable, every operator building LEO systems will have to create that bespoke management system for managing all of the complexity of spectrum, handovers, E node B in space, and maintain that, which increases the cost, which will end up being passed on to the subscribers. So by having a common framework, sharing those ORAN, XApps, RApps, we can drive cost out of the NTN satellite system and provide quicker, better service for everybody.
Yeah, and just to add one last thing, I think this maps well with the mission that we have in NTCS, because, so we're talking about NTN, there's also like non-3GPP access to integrate more legacy or existing satellite waveforms and protocols, but even what 3GPP defines, it's not sufficient to actually deploy a full system. And so what we are aiming to do in NTCS is basically take all of the other building blocks and understand how we can build actually interoperable solutions that can be reference platforms, if anything, to foster an ecosystem of vendors that may not be experienced in what we need for a non-terrestrial application, be it satellite or HAPS or whatever.
Yep.
You guys are getting ahead of my questions here. Okay. So here's one question for Erik here. What, out of this architecture, what are the interesting XApps or RApps, that we need to build?
So you mentioned an XApp for handover. I think that's probably going to be quite important. I think there'll be RApp functionality that's important to that as well, because you're going to know in advance that 5 minutes from now there's going to be another handover, and 5 minutes after that there's going to be another handover, and 5 minutes after that there's going to be another handover. So even a stationary UE is going to have experienced multiple handovers just sitting there. So
Assuming LEO, basically.
Assuming LEO, yeah. So you're going to have the service management orchestrator is going to have to predict all those topologies, issue all those commands going forward, and reroute all the traffic continuously to keep it flowing correctly. But the kind of RApps that you could build to monitor all of the performance. You also need an RApp actually to update the service, the SMO, for any changes in orbit, because it's propagating orbital motion based on its last data input. You need to have continuous input to tell it. Like we had to we had to change orbit because we were avoiding a collision or something like that.
Avoiding debris from a blown-up satellite.
That's
Yeah,
exactly
just
right.
read that today.
Yeah. So I think there's lots of work at that level to be done as well. And even to the point where we could finally get to some place where there could be orchestration among operators. It could be possible to know in a given SMO or a federated set of SMOs what frequencies are being used in what areas, along what pointing vectors. So you might be able to use the same frequencies or lease out your frequency to somebody else to use it in the same area, even if it does not destructively interfere.
So-
But that's very
Yeah.
hypothetical.
Very cool, potentially, yes.
Yeah, so the satellite folks, the NTN folks, we'll talk about handovers. These are satellite beam handovers or satellite handovers between satellites, because you can do beam to beam and you can do satellite to satellite as they move across the geography. That's not the same as a cell handover from a 3GPP point of view. So the UE on the ground is seeing the same 3GPP cell ID, same tracking area, but all this orbital dynamics, all of this spot beam and satellite handovers are occurring. They need to be orchestrated with the RIC function in addition to what's going on terrestrially with the 3GPP cell identifiers and tracking areas. So it's a two-level problem that you don't see in a cellular terrestrial network. You stay in the cell, you're attached to the same beam to the same base station till you physically move your UE. In this case, the UE stationary, you're doing cell handoffs and transitions between the satellites, but we have to keep the G node B context consistent so the core network is not seeing a bunch of trashing and slashing back and forth between E node Bs. The core thinks it's stationary, the E node B thinks it's stationary. All this RWrap is masking the satellite handovers from it. Very complex, but common with all of the LEO implementations and MEO implementations. The only place it doesn't occur is with GEO because the beam doesn't move. So having...
But the UE may move.
But the UE may move. So having a common solution that we could share among the operators would significantly reduce cost, improve performance, and over time, allow us to optimize spectrum sharing and other features because they interoperate.
Yeah, and as a last, just addition to that, like if you look at the parallel between GEO and LEO, you have to sort of like, both the GEO and the LEO are basically not just one base station, but they're essentially clusters of base stations. And on a GEO station, you may have like essentially one satellite serving a third of the planet coverage, which may be hundreds, if not thousands of cells. And similarly, a LEO may serve an area with a large number of cells. So you have to sort of unbind the concept of cell from a specific physical locality, from a specific physical item. So that's part of the things that we believe that the disaggregation and the ORAN applications can enable.
Mm-hmm.
Just curious, does 3GPP address that point of this idea of the virtual cell?
Oh yeah. They spent a lot of
NTN.
time about fixed cells on the ground, sweeping beams, stationary beams, how that affects lawful intercept, what happens when you cross a border, does your country code change, all the stuff that terrestrial operators have to worry about, but they kind of do it statically. We have to deal with on a dynamic basis, which makes all of this real-time, RAN control function a lot more fun, I guess, is one way to look at it.
Right. Okay, so a related question is, what are the gaps in Open RAN itself for addressing these applications? Like what's missing right now, from Open RAN? In terms of interfaces, et cetera.
I think the interfaces are pretty well defined. I think really what's missing is those custom R apps and X apps that are needed to do this next level of complex satellite-based orchestration and RAN real-time management. And that's why we're participating in this group, because the satellite industry is a long lead type industry. 3GPP does releases every 18 to 24 months. You get new base station functionality, hardware changes relatively quickly. We may specify a satellite today. It'll take 2 years maybe to build, a year to launch, and then have a 7-year lifespan. So our base station platforms that the software runs on have a 10-year or longer life cycle. So we're really looking at this for functionality that we're going to need in 3 to 5 years, and leverage all the work that's happening terrestrially and then leapfrog off of it. So it's not that, that the framework is solid, it's those applications have to be thought out, basically agreed upon by the operators, and then the software development innovators will then come to our rescue with a common implementation we can share.
Yeah, I think there's satellite network operators are going to gain a lot from 5G NTN by being able to move away from bespoke air interfaces and a bunch of other systems. But as you're moving away from like one set of bespoke systems, you could walk yourself into another set of bespoke systems for operators talking to each other, working with each other, and actually doing an open development so that all operators can interoperate is just a thing that just makes sense in 2022. So.
Yep.
Yeah, and maybe going even into the more specific elements. I mean, some of the, for example, E2 service models may need to be adapted for satellite use, or we may need to define entirely new ones. On the open fronthaul, I think most of it is already there, but the way that we're going to do distributed ground stations and distributed RAN for non-terrestrial networks, whether it's geo transparent, LEO transparent, HAPS transparent, or regenerative, where you have portions of it on the space or air platform, probably there's going to be some changes there. There's going to be some even minor adaptations that we'll have to do. And this is some of the stuff that we're looking into. And similarly on the, let's say, non-real-time to real-time RIC interfaces, there's probably going to be a lot to work on, because all the things that Erik mentioned in the beginning, like collision avoidance and prediction of, I mean, there's definitely, like, the SMO will implement them, but then some of these primitives and APIs will need to be translated to the RAN. Or even like one of the items in release 17 is the broadcast of ephemeris data in the system information to the UE. That stuff needs to be populated into the RAN, into the GNode B by something. And today, this is left completely to the implementation. So some of this stuff will probably, I suspect, will probably have to be solved.
Yeah, I think one of the, you bring to mind one of the things I learned recently about, there's an ITUR model for basically using the total electron count as a result of a sunspot activity to anticipate propagation loss through space. And like, once you observe a sunspot, you've got basically 8 minutes to replan for the anticipated predicted like total change in electron count. So you've got to move pretty quickly.
We're very familiar with that problem because our satellites often undergo these kind of issues. So.
So that's a very unique NTN related
big
thing.
flips.
Well, and to your point about systems having a lifetime, you can only fly space qualified hardware, which is not the same stuff that you can buy off the shelf today. It's considerably older.
That actually brings up another question that we had on here, which is there a need for new silicon, for the NTN?
That's a very good question. Potentially not, but the reality is that it's still widely unknown. So what Erik was just saying, the reality is that there's not a lot of silicon, especially newer silicon and high capacity silicon that is space qualified. And it typically takes a long time and a lot of money to qualify silicon and hardware in general for space use, which has impacts on all sorts of things. So there is maybe not need for new silicon. In fact, we would probably want to reuse as much of the silicon that is coming out for terrestrial applications, and we do already. But there is need for more effort from companies to do space qualification, to basically test the silicon in radiation environments and things like that. That's definitely something that we need.
Yeah, and it comes down to where you're flying your satellite. Different LEO, MEO, GEO has different radiation load, different particle issues from the sun, and today some of the nano satellites that have a year or 2 year lifespan, they're basically taking automotive qualified parts, throwing a little shielding around it, and that's good enough for 2 years. As you start looking at 5 to 7 to 10-year lifespans, then you're starting to talk about either really hardening an existing platform so that it can tolerate the temperature swings and shield it so that the electrons don't get blown through it, or having to spin new silicon. I think the biggest and most exciting thing that has happened to the NTN space is the advent of SDRs, software-defined radios.
Yeah.
That allows the NTN folks to behave a lot like existing terrestrial base stations. You can have a common payload bus with an SDR, and if it has the right antennas, you can do different frequencies. You can do different waveforms by loading software. That's a game changer. But we have to think about those components kind of in a 10-year lifespan. What SDRs, how much memory, how much processor speed, what level of shielding, so that over the 10 years lifespan of that craft, we can continue to upload new 3GPP functions, add additional real-time, applications to it to keep current with what our partner terrestrial network operators are doing, so that the services provided to their customers are seamless, ground or space. So it's very powerful to have a common, ORAN set of software packages that we may be able to leverage from the ground, tweak it for space, to continue the flow of enhancements and innovation in the NTN world.
Yep. And now that you bring up SDR, I mean, there's an area that it's not quite covered today by ORAN, but it's basically a lower layer split, let's say split 8 in a digital baseband fashion. So the way today, if you look at SDR-based platforms, you basically pass an IQ stream via Ethernet or IP to an SDR transceiver. And that allows you to do full multiplexing and A to D conversion waveform agnostically. And that's something that we are quite keen in the satellite space, because we operate multi-band, multi-channel with flexible channel allocations both on the ground and in space. So being able to have that sort of flexibility that we can take forward in many years of system lifetime, it's a huge advantage, both on the ground and in space especially.
Yeah, so you could run 3GPP, NB-IoT, 5G, NR. You could run LoRaWAN all at the same time using the SDR technology. So it's a very powerful, flexible way to put payload options with a common architecture on a spaceborne platform.
And especially if you do we do a lot of, at least in Inmarsat, we do a lot of government and even military applications. And typically these guys, they want to be able to do their own thing. And so alongside providing an NTN service to standard UE, you need to be able to also have that flexibility to allocate raw spectrum to custom things.
And this is where the ORAN gets interesting. Those type of customers, which could be enterprise, but DoD government, they may provide their own SDR image and their own ORAN executables that we as the platform provider are completely unaware of by design. Think of it as the next generation of hosted payload or condo satellite models that the government used years ago. Here they can run in a separate virtual machine, so to speak, on the spacecraft, their own SDR, their own software, the real-time RAN stuff, and we're completely unaware of it other than its power draw and cooling requirements from the whole bus. So it's a very powerful, almost like a cloud satellite architecture in space. But if we don't have the ORAN and these functions, everything will be bespoke, and that kind of defeats the purpose.
You could even have digitally signed XApps. So you could only run certified.
Yes,
XApp images.
there is a company working on that with DoD that is actually certifying not only that the apps, but the hardware is signed, so that you know the custody chain of where the parts came from that were built into the hardware and the software that's running on that hardware, and actually the data stream is also signed. So you can guarantee integrity end to end for critical stuff like that, which is a change because today it's encrypt at both ends and hope for the best in the middle. This is going to allow that to be secured end to end.
Okay, very interesting. One thing that we were discussing earlier is, we talk about like this new things like potentially new satellites, new buses, putting all kinds of fancy electronics up in space, but there are a lot of existing assets, particularly from the legacy operators, shall we say, right, that are not going away. So how do you integrate that, into a, not too crazy seamless architecture along with the new stuff that you get up there?
Okay, I can give the first answer since I feel sort of pulled into. So okay, there's a couple of things. So the first thing is that the existing architectures that we use actually have some advantages. So for example, our geostationary satellites are by and large transparent band pipes. They are a bit of they are intelligent band pipes. They're not like just bouncing the signal. So typically what you have on a payload is what we call a feeder link from a ground station. Then you may have like an analog or digital channelizer that takes the channels from the feeder link and then maps them to user link beams on the user link antenna, and filters the frequencies and allocates the cell offsets and so on. So what we found is that that architecture already allows you to implement NTN out of the box. So that's the first layer of integration. The problem on the ground is that if you're operating this alongside existing services, you need an architecture that can accommodate those. And that's why all these like interfaces, the RU-DU split, the CU-DU split. We operate systems that are half 3GPP in some way, but may have like a proprietary or modified physical layer. So if you can actually have like multiple RUs with different low-level PHY, for example, you can actually integrate that very easily. And so, I mean, there's other aspects, like for example, other payloads, like particularly in broadband, like a Ka band millimeter wave, so 27 gigahertz and so on. They tend to have large tube amplifiers that are analog and are usually driven close to saturation. So for waveforms like OFDM that tend to have a fairly high PAPR, peak to average power ratio, you may have a capacity hit on the payload. So if you can then have like an RU that you can modify and implement transparent DSP to compress the signal or additional digital predistortion, crest factor reduction, then you can enable those NTN services seamlessly without or minimizing at least that capacity hit on the payload. Newer payloads can be designed already with this in mind, but there's no reason why you would waste billions of dollars of investment in space.
I was going to say that, I mean, this is the problem of greenfield versus brownfield deployment is sort of well known in many industries. And I think even if you can't get the benefit of a data plane change, say, for an existing constellation, you might still be able to explore deploying control plane changes. So you might have newer style ORAN compliant service management orchestration going on, and it might actually not be talking directly to the satellites in orbit, but talking to a proxy agent on the ground that's understanding all of the new context and translating it into the old control plane messages. I think that's probably maybe the safest way to explore a brownfield transition.
Mm-hmm.
Yeah,
agree.
definitely.
Yeah.
Yep. Oh, go ahead.
Seamless integration also with let's say non-3GPP access and things like that through different layers of the control and management plane, for example, definitely.
So this may be, the answer may be obvious, but what seems exciting is that all of this stuff is talking about like direct to handset, direct to device, from space, which has not been available so far except for various, super bespoke, products. So how does this change potentially the business models? If everybody's using standard, 5G NTN or NB-IoT, applications that are the same from the user equipment point of view.
It's interesting. at least, sorry, I'll take the first.
Oh, go for it.
First. So for us, it's going to be a very significant change because today we specify the user terminal as well. We're not going to need to do that. We're not going to need to basically put out something that then gets built bespoke. We're part of an ecosystem, but it also means that the same UEs will work on a competitor's network.
Yeah, I think if you look at the value chain from the user equipment all the way up through the satellites and then the infrastructure supporting the satellites, one of the biggest issues with satellite systems in the past has been the user equipment. They're all bespoke, they're all expensive, and that's always been an impediment to large penetration. At an enterprise, never mind a consumer level, but even enterprises struggle with an Iridium handset cost and the minutes cost. What 3GPP has done is they have taken the handset out of the equation. It'll become ubiquitous. Anything that has a 5G capability will support NTN. So now the handsets are there in the billions potentially in 2030. That then shifted the cost and complexity problem to the platform. The beauty of bespoke UEs is you can define how good the antenna is, how that antenna works from pointing. Now you're in the consumer handset world. The antennas are not that good because they want room for cameras and other good stuff. That puts more responsibility on the network, the satellite, to be able to close that link and close it reliably. So it's going to change satellite architectures, which is physics. It's easy to do. But what it really starts to do is force the satellite industry to address the other large problem with satellite services: cost per byte, cost per minute. And we really have to drive the cost down, and we're doing that with smaller satellites, LEO orbits, rideshare launches. But what we haven't been able to really get our head around until now is having to spend millions and millions and millions of dollars in NRE on these bespoke control, management, and integrated payload software, and then the ongoing OpEx to keep that alive and train the people, because it's unique. If you work for Iridium, you're going to be familiar with their thing. If you work for Omnispace, Legacy would be their systems. SEI, all of them. Inmarsat, they're all a unique world. If we can come down to the point of getting the operating software and the real-time embedded eNode B to be disaggregated, to be commodity priced, we can then ride on the coattail of the Amazons and the other folks like Microsoft that are starting to do ground segment as a service. So we're starting to drive the cost out of the ground segment and the feeder link. We're hoping with O-RAN and the ability to plug and play and drive costs out with SDRs, that the satellite becomes more of a commodity purchase. And potentially you could have Condo with one SDR running Inmarsat software right next to an Omnispace, and now you've halved your capital cost to get just service in the sky. So that will then bring the retail pricing down to a point at which it's really a service that the average consumer would consider. It's not $5 a minute to make a phone call. It's getting it down to what maybe long distance was, international long distance was, 10, 20 years ago. So I think that, that's the kind of stuff that we're looking at as this NTN 5G and O-RAN stuff starts to really bear fruit, is to drive it into a true commercial service, affordable by the masses.
Yeah, and I think some of this will also climb back the ecosystem, because right now what we're targeting is basically the mass market, which is a novel market for satellite operators enabled by 3GPP and so on. But I suspect that, for example, some of these disaggregation interfaces like ORAN, SCF, like those front-end control, baseband interfaces, management interfaces, can also be used internally to future product ecosystem to ease the integration between component manufacturers, even in higher end use cases like aeronautical VSAT applications, maritime VSAT applications, and so on. So the reality is that today, in the satellite space, you have to either be able to do the whole thing, or just like individual component, physical component, and then very tightly integrate them together, often with very proprietary interfaces. Whereas here, like things like RF front-end control, beamforming control, these things can be sort of abstracted a bit more. So you can plug and play different components as well. So that will continuously drive down cost by opening up someone to do components that are a bit more like off the shelf. They can apply both to terrestrial and to satellite, and so we can just take those components and integrate them.
Yeah, and so, you know, we've been in conversations with the cloud players that are doing the telco solutions, and the ground station as a service is a very interesting concept, because the minute you put your ground station in a Microsoft Azure data center, you're now where the MNOs are running their cores, where the machine edge computing platforms are. Your latency to be able to run applications end to end through that terrestrial core start to drop down, and that brings some of the applications that previously were unimaginable, you know, less than 50 millisecond response times. So some of the real-time V to X stuff now becomes imaginable as a product that you could put on a LEO if your feeder link is in an Azure data center, or it's in a, you know, an Amazon data center with the rest of the telco facilities that are terrestrially being run in the cloud. So there are new opportunities that we really haven't wrapped our head around, because it's a paradigm shift. But it's coming, and we're hoping to be part of it and make it happen as quick as possible.
Yeah, and now that you mentioned cloud and like essentially cloud ground stations, Cloud RAN. For us, Cloud RAN is a way to compress that latency envelope as much as possible. But to do that, you need to be able to run components of the RAN in a cloud, private or hybrid or public. And that means digital baseband interfaces that are flexible, that allow you to insert things like channelizers and filters, and as well as all the application interfaces. And all of that, like especially the digital baseband disaggregation between components and common building blocks, so common CU, common DU, etc. All of that stuff can be enabled by ORAN and other Open RAN interfaces.
Yeah. So in 10 years, you may see the network as a service where all of the core network, all of the CU is running in an Azure or Amazon data center, just like the terrestrial guys. And a significant portion of the DU is hosted on a satellite to keep signaling control plane messages within the space for performance. And the majority of the up and down link is actually user plane. And you can see that architecture being very scalable, very high performance, very cost effective. Because one of the problem with legacy satellite is you make your capital investment and it's sunk. And you put a lot of money up front and then it depreciates. With the new cloud-based model, it's a pay-as-you-go. But Amazon and Microsoft, they're refreshing the servers. We're just running our stuff on it. And you start to get much more cost-effective, cost per byte served by doing all of that, along with major performance improvements and continuous integration, continuous deployment, all of the the new technologies for doing innovation in the cloud. And with software-defined radios and VM concepts, virtual concepts in the bird, you're uploading software there and keeping up with 3GPP releases. So it's an exciting time for the satellite, because we've always been kind of a leapfrog. Something was good in 1980, 15 years later you did the next one. We're not going to be, now we're going to be more like the rest of the world.
Yeah, it's funny because I think one of our networks, one of our oldest serving is based on actually 3G UMTS, or at least originated from 3G UMTS. And it's funny because when we deployed that, it was actually by a few months the first ever 3G network deployed. It wasn't even a terrestrial one, but by now the technology has moved on a lot, and it has basically diverged in different directions. We've moved in our own direction, and terrestrial has moved in its own direction. So now it's a time to actual convergence.
Yeah, and I think the last thing that I'll mention in this area, the satellite industry has been an offshoot, a very enclaved collection of vendors and personnel. In other words, if you're in satellite, you're in satellite. You're not going to cross over as a senior principal architect into an AT&T. What we're going to see in the next 10 years, along with all of this virtualization and the O-RAN, is it will be possible for an AT&T network engineer who specializes in O-RAN and these real-time applications to work at a satellite company, because it won't matter that it's a satellite. It's a RAN, and it's common technology, and it's common methodologies for building it, supporting it, and deploying it. And we're going to start to see more and more of the really good resources start to come into the satellite field that today have been either working for the big guys doing cloud stuff, who are now being absorbed kind of into the telcos as the telcos go through the cloudification, and we're hoping to benefit from them, that stream of, of resources to get their mind shared to kind of help us get to where we need to be.
Okay, very good. I think we can move on to some audience questions.
Okay, yeah.
Yeah?
Great.
So, anybody have any questions? Speak up. Yes.
Here we go. This is Claudio from Deutsche Telekom. I'm one of the operator co-chairs in Working Group 3 for near real-time RIC. I just wanted to understand, where do you see some more detail about the use case, for HAPS, right? I didn't follow, the work in 3GPP, so I don't know if 3GPP is looking at the architecture of NTN and how the satellite is seen, from an architectural perspective, if it is a logical node or not. But I was thinking, where do you see, because I heard HAPS and RAPS, right? But there are different control loops involved. So this reverse mobility that you were talking about, compared to the UE, so we are more here in the near real-time domain, or it's more an on-an-M use case?
Okay, so it depends. For example, for mobility and like inter-beam mobility, things like if you want the extension of your traditional measurement-based mobility, but you may want to have here an XApp that is specific for a satellite use case, for example, for a GEO or a LEO use case, and for that particular implementation of the beam layout. So, and then you may want to plug behind that a machine learning model that allows you to basically see, okay, typically how do I see the trend in signal due to, for example, fading and things like that. Because you have to think of it also in this way. A satellite beam, at best, can be like 25, 50 kilometers, but can also be like 500, 1,000 kilometers in diameter, depending on how you form your beam. And by and large, especially like in low frequency bands and so on, the way that the environment is shaped, like mountains and like terrain, can influence the way that the signal is registered by the UE, even if it's in the same beam on a very large scale. There are elements of the antenna of the satellite that influence that, like variations in the phased array. There are a number of things, interference from other beams, adjacent beams, or even adjacent satellites. So you need very specialized applications that go and look at the right elements. So for example, to avoid ping pong, but on a completely different scale, essentially, and with different parameters in mind. So that's where, for example, we would like to see some interesting developments, and being able to plug in both our own IPR, but also some other companies' IPR that may be developing predictive handover algorithms and things like that. So I don't know.
I mean, I was going to say that a platform itself can avoid its own interference and avoid pointing beams, across its own, depending on the shape of its platform. We had highly steerable beams on Lunar, and it was nearly possible to point it straight at another antenna if you weren't paying attention. But the global optimum of avoiding interference is something that you have to do outside of that platform.
Yeah.
So that's more.
So I guess my expertise is more in the core network and the OSS, BSS, but we have experts in the RAN area in our organization. And I think what they've been looking at in this area is, there's two levels. There's the cellular cell site identifiers that determine where you're at relative to the core network. And there's the beam and the sweeping, or how that works from the satellite. So they have to be managed independent, but they're dependent on each other. Our assessment is that the work that's being done in 3GPP as it pertains to massive MIMO and how these spot beams are being formed may have applicability to how we're managing our beams, because we're basically doing massive MIMO by forming these beams and doing handovers, and we believe there will be, with supporting and tweaking, reuse of that real-time code in managing our beams, because they're doing it today as they set up beams for individual UEs. And we think there's a lot of synergies there, because it effectively looks like a big MIMO system.
Yeah. Yeah, to some extent, yeah.
Yeah.
Okay, next question.
Satellites that have a mix of cellular integrated services like the ones you've been discussing and like non-cellular services like a typical, essentially the equivalent of fixed wireless access or broadband internet or a bunch of other things they may be doing? Or do you expect to essentially do 5G FWA, fixed wireless access, via satellite, or is that just unnecessary for sort of blending that? And where you've got these sort of multi-service satellites doing 5G integrated services and non-cellular services, how do you manage that mix?
Okay, so I can give a first shot maybe at this, because we are going to operate mixed service satellites, and this is going to be both for mobility, high mobility use cases in, let's say, low frequency bands, and also mobility and fixed use cases in high frequency bands. So the answer is we are going to have a mix, at least for operators like us that have existing space segment. We are going to essentially operate mixed different types of services, or even like commercial and non-commercial, like government type services. The way we manage them is to external systems that are not 3GPP specified, like Erik was hinting at before, that these functions need to be managed outside of the whole system, outside of the. So we will have things like the concept of beam management, for example, and channel management. So frequency allocations will be irrespective. There will be a layer that is completely irrespective of the radio access that you are using, and then you will have deeper layers that are more specific to the radio access that you're using.
Yeah, I mean, I agree 100%. And I think the simplest way that we're looking at it is, if you have 30 megahertz of spectrum, you would initially partition it, 3GPP service and non-3GPP. And then as the AI and machine learning operates, we would then dynamically spectrum share, move capacity, time of day, based on load, and use the real-time interface to reconfigure the payload to match what we're seeing from a user traffic profile.
Just one clarification. So, Luca, you said you would use your existing assets, of course, but can you share the same asset between services in space?
Absolutely. Absolutely. Absolutely.
Yeah.
And you can even go as far as to say the same frequency resource in time and space can be shared across different services. You may even have intermittent cells, for example, in certain low demand region that are multiplexed on the time domain, same space domain, same frequency domain with another service.
And in some environments, you may do S-band or L-band or KU, depending on how complex your satellite is. And that will change 15 minutes later when you're over a different geography.
In terms of like adjusting to demand, for example, we do it already today on our networks, because we have, essentially you have to think of it like this. We operate around the globe, which means that our demand basically spins around. And it's kind of weird, but it's basically how it works.
But I think that what we're looking at is taking that to the next level, that within the same spot beam, not somewhere else, at a different time of day, or within milliseconds in the same day, potentially reconfiguring if we see demand spike, using tools that
Yeah, and you may have like a UE that uses the same frequency bands but a different, or maybe an adjacent channel or same channel adjacent beam for a different waveform, a different type of service. they may generate interference into a 3GPP service or vice versa. You may have like a 3GPP access service that generates interference into something else. So you need something that is higher layer that manages this kind of stuff.
And that's the big ticket items, right? Big services, large chunks of bandwidth. There are other services like LoRa, maybe you do it in a guard band. You don't even bring up a separate, it's just there kind of like NB-IoT terrestrially. So all of those are possible, but they require real-time management and administration.
Wait, so I mean, it's the place where business policy also injects.
And regulatory
directly,
policy.
right?
Yeah, all of that.
So I mean, because you have certain contractual requirements for certain services in certain regions, right? And you're not going to cannibalize one for the other.
Correct.
So.
Yeah, so that rules engine operating outside would be regulatory rules based on country, business rules next based on your business arrangements, and then active traffic optimization based on the services in that piece of the world.
Next question.
Scare them off.
Yeah, apparently.
Well, I appreciate you guys showing up. I mean, there's lots of other things going on here, but I hope this is kind of giving you a little bit of insight into our strange little world and, an idea of, we're trying to keep up, trust us. And we're hoping that all the standards work, and the O-RAN is going to let us actually become kind of a peer player in how quickly things are going to move to 6G and beyond. So thank you.
Thank you. Thank you very much.
Thank you very much. Thank you.